Hi, my name is Lauren Klein. I teach sixth grade science and social studies at Jefferson Island Road Elementary School in New Iberia, Louisiana. And this is the first of two professional development screencasts I'm doing. The first one is for science, developing inquiry skills through labs, and the other one is developing primary source activities for social studies task assessments. These two screencasts are a screencast version of professional development I'm doing for teachers in Iberia Parish who teach science and social studies for grades 3 through 6. But if you're interested in doing this, pretty much any sort of science or social studies has applications for you. So let's go ahead and let's get started with this. Um, Objectives for this session. First one, you'll be able to understand the need for rigorous inquiry-based science activities. You'll be able to explain the connection between inquiry-based science activities and science tasks on state assessments for the purposes of this uh, professional development. We're talking about the state of Louisiana. You will be able to create a systematic plan for scaffolding knowledge in an inquiry based science activity. And you will be able to explore four types of inquiry based science activities. So, and you'll be able, if you're in the professional development session, you'll be able to practice one. So, who is your presenter? Well, I think I'm uniquely qualified for both the science and social studies. I have a degree in aerospace engineering. I am a real live rocket scientist. I studied aerospace engineering, worked on airframe systems and spacecraft design for one of my college degrees. I also have a history degree, which makes more sense in terms of our social studies session. Uh, I also have a master's in gifted education. One of my research fields that I'm looking into involves looking for characteristics of giftedness in science and social studies. And maybe one day I could spin it into a PhD. Um, and also, in my normal teaching session, I do a whole lot of STEM in my science class. This is me at a gifted camp teaching students how to, we were looking at alternative energy, and we built wind turbines that generated electricity. I generally wear a lab coat because that's what science teachers, awesome science teachers, should do. And when I was in high school, I may or may not have accidentally focused my lasers in a lab and may not have blown a hole in the wall. So I think I'm uniquely qualified to talk about labs and science activities and stuff like that. So why are we all here? Why are you watching this? Why are you watching this screencast? Why are you interested in this if you missed a professional development session? Well, here's why. This past school year, I could create this real fancy graph, but needless to say, for our school district, science and social studies scores in upper elementary school took a nosedive. And generally across the state of Louisiana, the test scores for the 2014 15 school year for LEAP and iLEAP in lower elementary fell as well. And this causes us to look and see what can we do in order to improve classroom instruction for this. I give surveys to my students before and at the end of the school year, and I ask them about science instruction. Science instruction is really difficult. It's unlike ELA and it's unlike math, and it's really unlike social studies. It's this really blend of activity and knowledge all put together. And one of my responses, one of the questions I ask my students is, why is science hard or why is science easy? I asked them what do they find hard about science? And I asked what do they find easy? And one of my students a couple of years ago said this, that's coming into my classes, that science is hard because I can't make pictures of what my teacher talks about in my head. And the thing is, there's so much information, there's so much vocabulary that we end up falling into the trap of just giving lots and lots of vocabulary and telling the kids to memorize it because that's what's going to be on the test and stuff like that. But as you can see from the student's response, they can't metacognitively understand the terms that we're talking about. They can't make the applications, they can't see it because it's a very abstract concept. And for students in grades 3 through 6, cognitively, they haven't really developed the ability to deal with abstract concepts like students in middle and high school can. Uh, and one of the things I asked my students was what makes science easier for them to do and helps them understand. And this is one of my eighth graders. When I used to teach eighth grade, this is what they told me. And they said that whenever we do experiments, I understand we've been talking about better than when we make our study guides with our partners. And I pulled out this quote because it's really interesting. These student responses are anonymous, but from the class period I pulled it from, it was my lower end in terms of achieving at the beginning of the year. But they all had an amazing growth on science at the end of the year. And what was interesting is that, the traditional ways that we have students study through, creating study guides and graphic organizers and stuff like that, for this student, understanding science better was not so much of using interactive study guides or anything like that, but rather it was simply the fact that they were able to do experiments and see the science that we were talking about. And in this case, I was teaching 8th grade earth science. So these processes and stuff we talked about all year long, they were able to understand it way better than by doing experiments than by simply going through vocabulary and memorizing in a traditional class idea. So this is really important because rolling into 2016-17 school year, the state of Louisiana will be aligning their grade level expectations with the next generation science standards. Uh, and this is a really important thing because there's a really big shift in NGSS. Uh, because what's going to happen is that we're going to have to change the paradigm of how we teach. Traditionally, we teach, nice rows, tables, interactive activities, read your textbooks, say your prayers, take your vitamins, all these good things that we've learned as teachers that we want students to do in order to be successful. And it's been generally successful on standardized tests. But the problem is NGSS has moved from a knowledge base, if you will, to more of a performance base. Whenever you read the next generation science standards, you see a lot of performance based expectations for students, which means we have to change the way we teach science from this to this, where students are working with labs and they're building things. They have engineering and design standards because one of the things brought up by scientists and industrial leaders is that students need to learn how the engineering and design processes, because engineering is simply applying science to solve real life problems. And so science is moving in the direction to more of an integrated science and engineering. If you hear about STEM, that's science, technology, engineering, and mathematics, and how all of these subjects all kind of work together. Now, I know you're hearing me say this, you're absolutely freaking out. Okay, let's take a moment, let's freak out, and then we're going to chill out, and then we're going to move on with this. Okay, I know you're freaking out. So, how do we get there? How do we get from that traditional classroom base to the science and engineering and doing and labs and all of that stuff? Well, state of Louisiana published the responses of characteristics of poor responses of students on their science tasks in grades 3 through 8, and as well as the EOC for biology for high school. And here's what students who scored poorly, here's 3 things. One, from the stimulus material, they copied information without adding any details of their own. They just kind of said, whatever. They didn't follow the instructions, and they didn't understand the concept. And this is interesting because for the state of Louisiana, the stimulus material is generally reading graphs, charts. They have to answer some multiple choice questions, and then they have to do some sort of drawing of a model and write in an extended response. And these are the characteristics of the poor responses for students statewide in the state of Louisiana. That these 3 things kept on coming up, which leads us to think about this. And this comes from one of the chief educators in the state of Louisiana Science Department, and that students need to address the answer prompt with appropriate applications, procedures, models, and other forms of scientific thinking. In other words, the way we're assessing students in Louisiana on LEAP and iLEAP for lower elementary and even middle school and high school with EOC is that they need to use scientific thinking skills, that the constructed response task portion of the test is specifically designed to test thinking skills. And these skills are going to be in GSS. They're going to be the design and engineering standards. So for students, generally it's about 15% of the test is specifically focused on this and a performance thing. So we need to work on this. One of the keys, one of the little hints about assessing for science for LEAP and iLEAP is that it's binary the way they grade it. It's either right or wrong. And if you know anything about the old rubrics for English and social studies, is that there was a bit of a judgment call that they wanted a bit of creativity or a bit of outside the box in order to get a maximum score. Not the case in science. In science, the questions are very clear cut for your constructed responses, your short answers, and your extended response. If they ask for three things, if it has all three things, it gets all the points. If it's missing one, they take 1 point off, so on and so forth. So, one of the things whenever you assess labs and things like this, and whenever you create tasks for assessments, is that you need to grade this way, that it's either right or wrong, it's cut and dried, either they have it or they don't. And it's something you need to tell the students and have them keep in mind. So I want you to consider the following with my good friend and fellow aerospace engineer Bill Nye. Um, you know, what is the way that we can assess or create a framework for students to do labs and inquiry activities that can help out the way students are going to be assessed? Well, first off, we probably needed an objective. We need to tell them what they will be learning about in words they can understand. For instance, this would be a great objective. In my own class, all of my objectives are written in kid-friendly language. They should be unambiguous. My rule of thumb is this: can I break it down to the point where my student can say the objective when their parents ask them, what did they do in school today? That's kind of my golden rule for writing directions and objectives. Is, can I write the rules or the objectives or whatever simply enough that when a kid gets on the bus and gets home and their parents are like, so what did you do in class today? They can say what they did in term, or say what they learned in terms of the objective, and they can just say it real easy. For example, we figured out what makes plants grow faster. That's a good objective. It's cut and dried, straight to the point, things like that. You don't want these long, drawn out objectives like the one I had at the beginning of this screencast. Like, for instance, modeling the days of our lives using survival analysis when designing and analyzing longitudinal studies of duration and timing of events. Um, by the way, I know you're like, you don't understand. Well, the joke is, of course, is that modeling the days of our lives, that's essentially the rest of the title. I know, corny. MacGyver doesn't even understand it. If you're doing a lab, you should probably give the students a material list. Tell them everything they need to complete the investigation, even the amounts. It sounds silly, but it's a good thing for students to get in the habit of, because they grow up into upper grades, especially middle and high school. Science's inquiry objectives will ask students to create experiments and get them used to, and they're going to have to list materials and amounts. So it's a good idea to do this. In addition, you want a detailed procedure. You need to tell them everything they need to do in clear and precise terms, even the amounts. Give them clear and unambiguous directions, just like the objective, very kid friendly. So what did you do? Well, we found out plants grow faster. Give the detailed procedure, so that, like, if the parent would be like, so how did you do that? Oh, well, we put plants in containers and we put this much sunlight or whatever, and they can explain it. Even the amount. The amount should be in metric, okay? I know for elementary teachers, you're still kind of used to using customary units and things like that. The language of science is math, and the language of measurement that we use in science is metric. And especially whenever you get into 6th, 7th, 8th, and in high school, metric is what's used in everything on assessments. And even in science as an engineer, we did use a little bit customary, but we got into the habit of using metric, especially if we dealt with anyone outside of the United States. And that's the thing about metric. When I realized I weighed nothing on the milligram scale, I was like, OMG. Okay? So you want to get into the habit of using metric. Okay? So if you're ever like, oh, what do I need for, what type of scale? Just remember Science Cat right here. 0 milligrams. Use the metric scale. Get students used to converting them from one scale to the other. You should also give the students some sort of background knowledge check. If you remember the scientific method, you usually do some sort of research. If you're doing a lab or some sort of activity, you need to have that relevant knowledge in order to create a hypothesis and move forward. What I generally do in my class, we have some sort of background knowledge check. See what the kids know about the objective. And before they actually do the lab, make sure they understand what's the scientific concept they're exploring. Okay? leading to probably one of the most important things in constructing some sort of inquiry-based activity is a hypothesis. You want to make the students write a hypothesis that can be tested using the materials and procedures given. This is a non-negotiable thing. The lowest level that's doing this professional development is third grade. I suggest third grade. You get the students starting to write a hypothesis. Um, I use in sixth grade, I use this, if and then. If whatever you're going to do the experiment, then what do you think is going to happen? And what you think is going to happen needs to be clear, unambiguous, and testable, that when the experiment's done, you can look and you can see if it matches. And if you remember, if is the independent or independent variable, what you're changing for the experiment, then is the dependent variable, what you're going on in there. And I suggest that every single inquiry-based lab activity you do as a teacher, you should have your students writing a hypothesis. Get them used to it. I'll tell you, in my own experience class, I get some wonderful students coming from fifth grade that they kind of have a handle on it already. And by the end of the year, when it comes time to write a hypothesis, I usually don't even have to go over it because my students are just pumping out a testable hypothesis for their labs, which is really good and really encouraging. You should have scientific record taking. Make the students complete detailed observations during the experiment, and this depends on the activity. There should be tables for counting, or graphs, or drawings for creating scientific models. Whatever an inquiry-based lab activity should be that you're doing, that should be what sort of scientific record taking should be able to be clear, easily tabulated in order for you to draw conclusions on. And speaking of drawing conclusions, a good inquiry-based science activity should make the students evaluate their hypothesis and share findings using the observations. Okay, Common Core is all about using data in order to support a thesis. Okay, for ELA and by extension social studies. For science, we want to use experimental data to prove our hypothesis was correct. Or if it wasn't correct, what data did we do during the experiment that contradicts our hypothesis and that draws us to rewrite our hypothesis and things like that? Okay, science tasks will oftentimes ask students to create an experiment. Okay, and this drawing conclusions is kind of the tying up point. Okay, and drawing of the conclusions helps them when they come to create an experiment. They can talk about what happened, or during a science test, they'll give an experimental results with data, and students have to draw the conclusions from it. So this is a very important skill for teachers to teach students, and for students to master. And to be honest, when we do labs, a lot of times we kind of forget it because we run out of time. Okay, now that wasn't so hard, was it? Okay, so we walk through the scientific method in creating this inquiry-based lab activity. And so the steps in creating a lab-based classroom, remember, we want to shift from, vocabulary and study guides and stuff to inquiry-based labs. So how do we do it? Now, I know whenever you think about labs, you're thinking like, man, I'm herding cats, okay? There's kids everywhere, there's explosions and chemicals and stuff like that. It's not quite like that. Okay, it can be like that if you're not prepared, but with some preparation and planning and going through step by step, we can go there. Now, I want to take a brief time out with this while we watch cats being herded, is talk about this paradigm right here, okay, of the steps that we can go in order to create a lab-centered classroom. And I want you to think for a minute and look at this, evolutionary timeline, if you will, and see, where do you fall in your science instruction? Whenever you want to show a scientific principle to your students, do you show some sort of video to do it? Do you use virtual labs or simulations? Do you use lab demonstrations? Do you have the students do labs, or you even do project-based learning? And so I want, whether you're viewing this for the first time or you're viewing it as a review, or you're not even from my school district and you found this on YouTube, is I want you to look at this graphic right here and be reflective of your own teaching. I want you to find where you're at and see where you can move forward. Even if you don't even do video labs, this is a place to start. If you're doing student labs, well, you can move forward and do project-based learning. So no matter where you're at on this scale right here, there's something you can get from here, and I will as we go through this. Okay, so step one is video labs. That's the first step in introducing scientific inquiry. Is the old-fashioned concept of video in class. It's great because you can show it, the kids can watch it, we can do things, we can watch videos of stuff that we don't have in the class. One of the things is they need to be short. Okay, you need to find a video, even if it's a 20-minute long video. Find the amounts of time that you need for the experiment. Okay, watch the video, write down the equipment, fill out the procedure, everything like that, just like we were doing the lab in class. And during the lab, go over the procedure, show the video, okay, which is what's awesome. You can look at the concepts that can't be duplicated, and you can go through the lab just as though you were actually doing a lab physically in there, okay? Draw the conclusions, discuss the answers. You can always rewind the video and show important parts. Say, hey, when we're doing an experiment, this was the key point of the chemical reaction, or this is a key part of thunderstorm formation, or something like that. That's one really good thing about the video. Not so awesome is video labs are not very interactive and they can be boring. And also, you're kind of tempted to show like the 20-minute long thing just to eat up class time and stuff. That gets students disengaged from the lesson and it kind of draws away from what you're trying to do. It's not so much entertaining and showing a video for a concept when you do video labs. It's you're doing a lab, but the lab's being done on a video so everyone can observe it. And sometimes for the more experienced class, video labs can still serve a purpose. For example, you can find videos of labs where they don't go as planned and have students troubleshoot the videos in order to make it go the way it's supposed to. Okay, so that's video lab. Step one, you show the video in class, you fill out the lab sheets, you can observe and do that, but it's kind of on the screen and it's kind of disengaged from the students. Step two is a virtual lab, which in this day and age of technology is really awesome. Simulations allow students to complete an experiment with little or no actual materials. You find a program on the internet, you download it, and then you cut loose with the kids doing it. You can find what you do is, of course, you find students complete these investigations without equipment or materials. You just find the program like PHET, P-H-E-T. That's phet.colorado.edu. It's a great resource for simulations. Whichever Basel textbook you use probably has virtual labs. You can look around for in Glencoe Labs and McGraw-Hill and stuff like that. They usually have their labs outside of their subscription wall that you can pull them and use that. Or even if you have iPads or Android tablets in class, if you use some sort of virtual server, you can put it on the screen for students to watch while it's doing that. Pass out the lab sheets, go over the equipment list just like you would a regular lab, cut the kids loose. If you have only one computer in the class we can use, we can have the students go up with an interactive whiteboard or something like that and do the lab where everybody can watch. Or if you have your individual computer workstations, you can use that. Now, there is a downside to simulations. Usually simulations can be complicated, especially for lower elementary, because a lot of these simulations are geared toward, especially PHET, toward middle and high school. So there's all sorts of options. And knowing 8, 9, and 10-year-olds, all they want to do is push buttons and click on them. So what ends up happening is they get off focus of the activity, instead playing around. Now, for your advanced students, you can get the lab done and then let them play around and do changes and stuff like that. But be sure, especially for younger students, for your simulations, limit the options as much as you can, because you want them to focus on the science instead of doing that. So that's step two. Step two, you have simulations. Okay, so now we're kind of getting closer to reality, if you will. We've watched the video. Now we're kind of interacting with technology. Step three is, of course, lab demonstrations. Lab demonstrations is kind of what we think of when we do science. Okay, it's science. It's the real stuff. But let me get on my soapbox right here and let's talk about lab safety, since we're now actually dealing with stuff in the classroom. Okay, lower elementary, you might be thinking, really, we're mixing vinegar and baking soda. This isn't really important. Nobody can really get hurt with it. Well, time out, okay? As someone who's taught science for several years in high school from 6th through 12th grade, and being an engineer and working in labs, safety is first, last, always, especially where we're at in South Louisiana, the oil field, you see safety everywhere. And I want to get on my soapbox and talk about lab safety and establishing a culture of safety in your class. Because even though the labs aren't usually hazardous, lab safety should be taught to establish good habits. Especially grade level expectations for Louisiana require students to know about lab safety. And whenever they get into middle and high school, lab safety becomes extremely important. So it's good to get them into the habit. In my class, we always wear safety glasses for whatever we're doing. Whenever I say we're doing a lab, students put on safety glasses. And anyone who walks into my classroom must put on safety equipment in order for them to go, which led to a time when someone from the school board office walked into my classroom and to observe me, and one of my students stopped the entire class because they weren't wearing safety goggles. And it was a breach of lab safety in our class. And the entire class of 30 students stopped what they were doing and waited for the person from the school board to put on safety goggles. They were quite impressed by it, but the point is, I taught my students, and they really authentically made it their own, that safety is actually important in the classroom, and that anybody who comes in during a lab activity or anybody who participates must be safe. So what are some things? Well, one, you need safety goggles. Safety glasses for lower elementary is pretty much, yeah, a perfectly safe bet because you're not dealing with a lot of splash and a lot of liquids. Um, Middle school, of course, you want to do goggles, especially dealing with chemicals that splash. But in my experience, safety glasses has been fine. Your dollar store, places like Dollar Tree and things like that, sell safety glasses for $1. Buy a class set. It's not that expensive. And for students who wear eyeglasses, get spare safety goggles for them to wear because they can wear over them. As a teacher, you can wear safety goggles, especially when you do lab demonstrations. And if you're doing it all day, comfort becomes paramount. I personally wear UVEX glasses that are high, they're kind of proof against everything, but they're also comfortable to wear all day. They can cost anywhere from 13 to 20 bucks on Amazon. And you might be thinking that's way overkill for doing upper elementary. But in my experience for teaching 7 hours a day, and then you wear the goggles for 2, 3, 4 hours at a time, you don't want them to fog up. You want them to be comfortable on your face. So that's important. The next thing is some sort of protection for your clothing. Like I said at the beginning, I wear a lab coat because lab coats are cool, and I'm a science teacher. Therefore, I'm a cool science teacher. You can wear a lab coat, but you're totally stealing my style. But whenever you're doing a lab, you can wear some sort of protective clothing. Lab coats are good if something splashes, it ruins the lab coat instead of your fashion. But for the students, you could spend money on aprons. You could buy them lab coats if your science department is unlike mine and rolling with money. Or you can do what I do in my class is I get old T-shirts with usually adult extra large size. This is I'm teaching in elementary. So they're big enough to be floppy over the students' uniforms. And I give those to the students and they wear them. And at the end of the lab, at the end of the day, I collect all the t-shirts, I take them home and I wash them. And we can reuse them. So through 4 years of using them, I still only have a couple permanent stains on them. So the old t-shirt kind of thing really works for me in my class. So you might want to consider that. Um, Rubber gloves are optional, but if you have students who are really icky, if you're doing kind of a gross experiment, you might want to invest in them. As a teacher, I use thick gloves. I use actually dishwashing gloves because they're thick enough that even I do some dry ice experiments, for brief contact with the dry ice, it's insulated enough to keep my fingers from getting too cold. But if you deal with anything like liquid nitrogen and stuff like that, there are specialized gloves you want to use. But I found that the thick gloves work best and reliable. So, also where we were just talking about lab gloves, wearing gloves for that. Also, some other things you want to keep in mind as a teacher is wearing closed-toed shoes and dealing with chemicals. If you have longer hair, you might want to pull it back. So that's it for my soapbox. We now return you to your presentation where we're talking about that. Lab demonstrations let the teacher perform real experiments with only a minimum amount of equipment. What I mean by that is you have a lab experiment that you want to show the kids that's like really good and really goes with your objective that you want to do. but you might have something expensive, an expensive material. Like, for example, I use dry ice. We talk about sublimation. Well, a pack of dry ice is $11, for 2-3 pounds. And having to get dry ice for 60 students, that kind of gets pricey. And I know no one's like me as a science teacher, never pays out of their own pocket for science experiments. So what demonstrations are really good is for people like me, I know I'm the only science teacher who pays out of their pocket for lab supplies, is that it's really inexpensive. You can buy like one little container of something that might be pricey instead of having to buy a whole lot of it for students to do in the class. And it lets you do real science without the cost of having the students complete the time themselves, especially if you're paying for the lab equipment, like I said. You can find good demonstrations all over the place. You can look all over. I have links in the show notes that I'm going to post at the bottom. You guys can look for that. You want to try out the lab, of course, before you do it. It lets you do stuff like this. Poor guy, not following lab safety instructions, wears his goggles. It allows you to do stuff like this in the class. Your lab demonstrations, you kind of, especially when you do labs, you want to do like the wow factor, like, holy cow, look at what this did. This is an exothermic reaction. And it allows students to make direct observations and participate as well. Don't hog all the fun with lab demonstrations. Get the kids to come up and do the individual steps. And while the kids are doing like step 1 of the experiment, have your volunteers, you can talk about the science and help them make observations, okay? Because the kids are going to want to do science. Once you're like, hey, I'm doing a lab, get them to put on the goggles or glasses, get them to put on the lab shirt and the gloves, and like, okay, I need you to do this step. Can you do this for me? And then they do it, and they're like, wow. They go home like, wow, we got to do science. We got to do this lab, and they got to participate in science. It got to participate in an experiment, and you only did it once for the entire class. One of the other things I do in my class is I have cameras set up that I can show what's going on my interactive whiteboard so everybody can see what's going on. Now, what isn't so awesome is if you don't practice the demonstration beforehand, the results might not be what you expect. Now, I know you think, oh, Lauren, you like always are prepared. You've never done an experiment that went wrong because you didn't practice it. Of course, I've never done that. But seriously, you do want to practice it the afternoon before or the week before and make sure all the materials are there in the morning. And if it doesn't go off the way you expect, even though you practiced it, just, let the students troubleshoot and figure out what it is. And like I said, you want your labs to be like really, big, especially when you do labs with the students actually doing in the next step. Make your demonstrations big and the kind of things that I as the teacher am doing the lab demonstration because it's like too big and awesome for you guys to do as students. So it kind of keeps that specialness, if you will, to a lab demonstration and keeps the kids engaged. Step 4. Now we're getting somewhere. We're talking about student labs. This is what we think of when we think of science classes. The students are paired up, they're at their lab tables, they're doing the experiments themselves. And lab experiments, there are so much research showing that students doing lab experiments are the best indicator of success as a scientist and also on scientific assessments. Okay? That's why we do it in science. It allows them to directly observe, and they can talk with their peers, and they do the science themselves, and they're not being passive, they're actively doing it. They're directly doing the science process. Okay, and the key is finding the experiment where the students can recreate a situation where observations relevant to the scientific concept can be seen. That's the thing. You pick the lab and you make sure it's exactly what you're teaching so the kids can see it in action. Going back to what my students said in the survey was that experiments are great because it allows them to understand what's going on. They can make those pictures and make those connections that they need in order to understand it. Students get them to experience science and the inquiry process firsthand. When students come into my class, that is what they say. Oh my goodness, Mr. Klein, I cannot wait for your class because you guys do science experiments all the time. In my class, we do 1 lab experiment per week as 6th graders. Okay, sometimes if I push it, I'll do 2, depending on the concept. And I'll usually do a lab demonstration thrown in between. So my kids know once a week we're doing a lab about some sort of important information that we need to know. And in addition, I assess them on it. Uh, During the lab, of course, you want to go over lab safety and you want to monitor the class and you want to so you can walk around and question the students to make sure they're getting the information. Now, not so awesome. Now, let's be real when we're talking about experiments. No matter how much you try, students will pester you, okay, if they're doing it correctly. Please don't just give them all the stuff and say, have at it, even though they have the instructions. Go over the instructions until they are comfortable following instructions and go. And the thing is, no matter what, no matter how much you try, students will still pester you to see if they're following directions. Because, sometimes even drinking water is difficult for some students. Bless. We love them. But those students in your class, you give the instructions, you go over it, you model it, and they're like, teacher, I don't know what I'm doing. Okay? No matter what happens, you're going to have those students. The key is whenever you're facilitating a science experiment in class is to ignore those students and tell them, why aren't you following the instructions? And have their lab partner look over that. Okay? So that's the science lab. It's kind of like doing lab demonstrations, but all the students do it. Once everybody's done with the experiment, you want to bring everybody together in order to go over, the conclusions and stuff and see if conclusions are off. And a good way to extend the science lesson right there is if students come up with different answers and you troubleshoot what happened, because what ends up happening is you're gonna, especially if you do experience with labs, is you have a couple sets of students, they don't follow the instructions and the results are like completely different than everyone else. So there's the teachable moment. Why are students X and Y, why are their results different from everyone else? And what's going to happen is one of your students, a light bulb's going to go off and they're going to be like, well, because students X and Y didn't follow instructions. And so that goes into what's so important about science is science is repeatable. That's why we do our instructions and stuff so detailed and things like that, so you can repeat the results of the experiment. So the promised land, okay, I can tell you as a teacher, I'm just now getting comfortable with the promised land, okay? Congratulations, you've made it, okay? Only in the past year or so have I really gotten into the swing of doing lab experiments consistently once a week. Getting kids together, drawing conclusions, and really making it work, okay? So, even I, as a teacher for the past 8 years, I've only really now just gotten it, okay? And a lot of these experiences I'm telling you in this presentation is from what I bring in my class. The promised land is project-based learning. That's where my next big push is. And once you get student labs, this is where you bring project-based learning into things, okay? And you want to bring it in because project-based learning with next generation science standards, the engineering and design standards really comes into play. You allow the students to apply the scientific method to solve a real-life problem. That's engineering. So you can really bring in the engineering and design standards through project-based learning. My students do one project per 9 weeks. 9-week grading period. The biggest one, the most famous one at my school are the balloon-powered cars. Every January on the second Friday of January in the school year, the 5th and 6th grade hallway just turns into this chaotic zone and it gets covered in painter's tape as my students have, over Christmas break, built balloon-powered cars because that's what we use to explore Newton's 3 laws. And they have their procedures, they have their rulers, they have their tape measures and stuff like that. And they spend all day long, each class period, they're 2 hours of class. They race their cars, they have to tweak their cars, they get the information, and then they spend the next week coming up with conclusions for the information for there. Okay, so they engineer it, and it's really interactive. They all love it to the point where I actually now have to give the project before Christmas. So they get the 2 weeks of Christmas break and then a week of 2 weeks of class before they do it. So they end up having a month on it. And what's really great whenever you create these really interactive science projects is that students buy in so well that what ends up happening is the design process of, oh, well, the design doesn't quite work, so I need to go back and revise it and fix it. They end up doing it themselves. And you end up with crazy things like one of my students this past year was actually racing his balloon-powered car down the aisles of Walmart late one night with his father because they couldn't find a place that had long enough straightaways for them to race down the aisles for the car. And so this gets the kids involved, and it gets them more than just observing the science. It allows them to see how science can solve problems in the world, because that's what we want. We want more engineers, okay? We want more independent thinkers. We want more problem solvers, especially problem solvers, because, engineering and the sciences depending on the point of view you hear, is kind of a crisis of people majoring in engineering that, and the sciences, that there is a need for people like that. But even if your students aren't going to become engineers, you want them to be problem solvers, because as a teacher, you have problems you solve. Accountants, you have problems you solve. Even janitors, and service people, for those students that are never going to go to college. We know they're in our classrooms. They're not going to go to college, but giving them the design and engineering and thinking skills that whatever job they go through in life, that if they see a problem in their job, we've given them the opportunities to apply problem solving skills in order to solve them. And that's so important for that. So thank you very much for going through this presentation. I hope it was really informative and informational for you. I have the full guides that I wrote for science and social studies. For the social studies video, I'll have it there. I have the full guide for science that includes all of these notes and all of the information. For the lab, includes links to some places where you can find lab demonstrations and simulations. And since this is on YouTube, as always, if you have any questions, you can post them in the comments. If you have any thanks or anything like that, please let me know. Please share this if you're from outside of my school district. I have it on YouTube for everybody to see what I do in my classroom and hopefully become better teachers so we can make better students. Thank you so much for watching.